Changes in mechanical and fluid systems can be uniform or non-uniform. In mechanical systems, a uniform change is a constant speed, while a non-uniform change can be a vibration coming to rest. A uniform change in a fluid system is the constant flow rate of a pump. While a non-uniform change can be the outward flow of gas from a sealed tank. Time constants are used to calculate and predict how long these non-uniform changes will take to be complete. Let's start with mechanical systems. A constant rate, such as speed, is uniform and will produce a straight line on a graph. A vehicle traveling at 100 kilometers per hour will cover 100 kilometers in the first hour, 202, 303, and so on in a linear way. This vehicle would cover 2,400 kilometers in a 24-hour day. A variable rate of motion, such as a vehicle that triples its speed every hour, is non-uniform and produces an exponential curve on a graph. Starting at 100 kilometers an hour, it would be on its way to a universal speed record. In the first hour, it would cover 100 kilometers, the second hour 300, the third 900, and so on, so it would cover 8,000 kilometers in less than 5 hours. In 24 hours, it would cover 850 billion kilometers. That's quite a vehicle. It would have to travel faster than the speed of light to do that. This is a non-uniform exponential change in speed. When the change is represented by an exponential curve, the curve becomes a tool that enables you to find the time constant in that system and predict how long it will take for the change to be completed. A common non-uniform change in a mechanical system is a vibration that's coming to rest, such as the changing motion of this diving board after the diver's been launched. The board is displaced a considerable amount when the diver jumps on it. After the diver takes off, the board vibrates up and down several times. Then eventually the vibrations die out. This is called damping. If we plot the distance that the board moves over a period of time, starting with its maximum displacement, we see an exponential decay in the motion of the board. The board moves less and less on each bounce. The graph shows the curve that slopes sharply at the beginning, then slowly levels out, a nonlinear change. Calculating how long it will take for the board to stop vibrating, or dampen, means finding the time constant. After 5 time constants, the process is 99% complete. Using time constants to calculate how long damping will take is important in structures, such as aircraft wings. The forces acting on the wing are so large that it has to vibrate in order to dissipate the energy. If you have a chance to fly, you might notice how much the wings of a large airliner move up and down. One way to prevent the vibration is to make the wings stronger and more rigid, but that would make them so heavy the plane would never get off the ground. Wings can vibrate, but these vibrations have to dampen within a certain time. Otherwise, they could develop into destructive proportions. Finding the time constants of the vibrations enables technicians to predict how long the vibrations will take to dampen out. Much of this calculating is done on scale models in laboratories before the real aircraft even take to the air. Measuring the intensity of vibrations and calculating the time constants for a commercial airliner is the job of Shig Nishita.
What we have here is a model of a nacelle and wing of a 757 airplane. Airplanes are subjected to a phenomenon called buffet, or flutter, or vibration. As you notice, when I vibrate this nacelle there, it also excites the wing tip also. So we put it on here, we put this accelerometer on the side of the cowl here. And using that accelerometer, we measure it on this strip chart. So I demonstrate by going like this, and we'll put it on the strip chart over here. And you can see the vibrations on the strip chart. And looking at that, then we can measure the slope of the decay to tell us what the damping is for that spring. Now, if the spring damping does not match what was required by the aerostaff, well, then we'll put damping material on the spring to change the damping.
Now let's look at how time constants are used in fluid systems. Pressure causes a fluid to move. The flow rate of a fluid, such as through a pump, is the volume moved in a period of time. A pump usually operates at a constant pressure, so its flow rate is easy to measure. If the pump is operating at a constant flow rate of 100 gallons per minute, you can safely predict that in 10 minutes, 1,000 gallons will move. That's a uniform change and produces a straight line on a graph. Now suppose the tank is sealed, like this scuba tank. When the tank is filled, the air is squeezed, and this increases the pressure inside the tank. If the pump operates at 1,000 psi, the flow into the tank will be fast at first because of the pressure difference. But soon, the pressure inside the tank approaches 1,000 psi, so the flow rate slows down until the pump can move no more gas. The flow rate of the pump decreased in a non-uniform way and makes an exponential curve that approaches but never reaches a maximum pressure. Finding the time constant from the curve shows how long it will take to fill the tank to capacity. If the air is released from the tank through a straight valve, the flow rate decreases exponentially because the pressure inside the tank continually gets lower as the tank empties. Knowing the time constants of non-uniform fluid systems enables technicians to calculate and predict how long it will take for the changes to be complete. In mechanical systems, time constants enable technicians to calculate and predict when non-uniform mechanical changes will be completed. If you've ever driven in a vehicle with worn shock absorbers, you know how it just keeps on bouncing with every bump. Springs alone tend to take a long time to dampen out. Shocks are designed to reduce the damping time of the spring. Tall buildings sway in the wind. Their damping time must be calculated by engineers so the occupants of the building don't get seasick. In other words, time constants turn seemingly unpredictable changes into predictable ones, except in television where we can do anything we like with time.